Fluid attenuated inversion recovery, FLARE, is an MRI sequence with an inversion recovery set to null fluids. For example, it can be used in brain imaging to suppress cerebrospinal fluid, CSF, effects on the image, so as to bring out the periventricular hyperintense lesions, such as multiple sclerosis, MS, plagues. It was invented by Dr. Graham Bitter. FLARE can be used with both three-dimensional imaging, 3D FLARE, or two-dimensional imaging, 2D FLARE. Technique. By carefully choosing the inversion time, TI, the signal from any particular tissue can be nulled. In the case of CSF suppression, one aims for T1 weighted images, which prioritize the signal of fat over that of water. Therefore, if the long TI, inversion time, is adjusted to a zero crossing point for water, none of its signal is visible, the signal of the CSF is theoretically being erased from the derived image. Clinical applications. The FLARE sequence analysis has been especially useful in the evaluation and study of CNS disorders, involving lacunar infarction, multiple sclerosis, MS, plagues, subarachnoid hemorrhage, head trauma, meningitis and other leptomeningeal diseases. Paramagnetism. Paramagnetism is a form of magnetism whereby certain materials are weakly attracted by an externally applied magnetic field, and form internal, induced magnetic fields in the direction of the applied magnetic field. In contrast with this behavior, diamagnetic materials are repelled by magnetic fields and form induced magnetic fields in the direction opposite to that of the applied magnetic field. Paramagnetic materials include most chemical elements and some compounds. They have a relative magnetic permeability slightly greater than 1, i.e., a small positive magnetic susceptibility, and hence are attracted to magnetic fields. The magnetic moment induced by the applied field is linear in the field strength and rather weak. It typically requires a sensitive analytical balance to detect the effect, and modern measurements on paramagnetic materials are often conducted with a squid magnetometer. Paramagnetism is due to the presence of unpaired electrons in the material, so all atoms with incompletely filled atomic orbitals are paramagnetic. Due to their spin, unpaired electrons have a magnetic dipole moment and act like tiny magnets. An external magnetic field causes the electrons' spins to align parallel to the field, causing a net attraction. Paramagnetic materials include aluminium, oxygen, titanium, and iron oxide, FeO. Unlike ferromagnets, paramagnets do not retain any magnetization in the absence of an externally applied magnetic field because thermal motion randomizes the spin orientations. Some paramagnetic materials retain spin disorder even at absolute zero, meaning they are paramagnetic in the ground state, i.e. in the absence of thermal motion. Thus the total magnetization drops to zero when the applied field is removed. Even in the presence of the field there is only a small induced magnetization because only a small fraction of the spins will be oriented by the field. This fraction is proportional to the field strength, and this explains the linear dependency. The attraction experienced by ferromagnetic materials is nonlinear and much stronger, so that it is easily observed, for instance, in the attraction between a refrigerator magnet and the iron of the refrigerator itself. Relation to electron spins. Constituent atoms or molecules of paramagnetic materials have permanent magnetic moments, dipoles, even in the absence of an applied field. The permanent moment generally is due to the spin of unpaired electrons in atomic or molecular electron orbitals. See magnetic moment. In pure paramagnetism, the dipoles do not interact with one another and are randomly oriented in the absence of an external field due to thermal agitation, resulting in zero net magnetic moment. When a magnetic field is applied, the dipoles will tend to align with the applied field, resulting in a net magnetic moment in the direction of the applied field. In the classical description, This alignment can be understood to occur due to a torque being provided on the magnetic moments by an applied field, which tries to align the dipoles parallel to the applied field. However, the true origins of the alignment can only be understood via the quantum mechanical properties of spin and angular momentum. If there is sufficient energy exchange between neighboring dipoles, they will interact, and may spontaneously align or anti-align and form magnetic domains, resulting in paramagnetism, permanent magnets, or anti-ferromagnetism, respectively. Paramagnetic behavior can also be observed in ferromagnetic materials that are above their Curie temperature, and in anti-ferromagnets above their Néel temperature. At these temperatures, the available thermal energy simply overcomes the interaction energy between the spins. In general, paramagnetic effects are quite small. The magnetic susceptibility is of the order of 10�3 to 10⁵ for most paramagnets, but may be as high as 10�1 for synthetic paramagnets such as ferrofluids. Delocalization. In conductive materials, the electrons are delocalized, that is, they travel through the solid more or less as free electrons. Conductivity can be understood in a band structure picture as arising from the incomplete filling of energy bands. In an ordinary non-magnetic conductor, the conduction band is identical for both spin-up and spin-down electrons. When a magnetic field is applied, the conduction band splits apart into a spin-up and a spin-down band due to the difference in magnetic potential energy for spin-up and spin-down electrons. Since the Fermi level must be identical for both bands, this means that there will be a small surplus of the type of spin in the band that moved downwards. This effect is a weak form of paramagnetism known as polyparamagnetism. The effect always competes with a diamagnetic response of opposite sign due to all the core electrons of the atoms. Stronger forms of magnetism usually require localized rather than itinerant electrons. However, in some cases a band structure can result in which there are two delocalized subbands with states of opposite spins that have different energies. If one subband is preferentially filled over the other, one can have itinerant ferromagnetic order. This situation usually only occurs in relatively narrow, d, bands, which are poorly delocalized. S and p electrons. Generally, strong delocalization in a solid due to large overlap with neighboring wave functions means that there will be a large Fermi velocity. This means that the number of electrons in a band is less sensitive to shifts in that band's energy, implying a weak magnetism. This is why S and P-type metals are typically either polyparamagnetic or, as in the case of gold, even diamagnetic. In the latter case, the diamagnetic contribution from the closed shell inner electrons simply wins from the weak paramagnetic term of the almost free electrons. D and F electrons. Stronger magnetic effects are typically only observed when D or F electrons are involved. Particularly the latter are usually strongly localized. Moreover, the size of the magnetic moment on a lanthanide atom can be quite large, as it can carry up to 7 unpaired electrons in the case of gadolinium, 3, hence its use in MRI. The high magnetic moments associated with lanthanides is one reason why superstrong magnets are typically based on elements like neodymium or samarium. Molecular localization. Of course, the above picture is a generalization as it pertains to materials with an extended lattice rather than a molecular structure. Molecular structure can also lead to localization of electrons. Although there are usually energetic reasons why a molecular structure results such that it does not exhibit partly filled orbitals, i.e. unpaired spins, some non-closed shell moieties do occur in nature. Molecular oxygen is a good example. Even in the frozen solid, it contains d-radical molecules resulting in paramagnetic behavior. The unpaired spins reside in orbitals derived from oxygen p wave functions, but the overlap is limited to the one neighbor in the O2 molecules. The distances to other oxygen atoms in the lattice remain too large to lead to delocalization, and the magnetic moments remain unpaired. Theory. The Boer-van Leeuwen theorem proves that there cannot be any diamagnetism or paramagnetism in a purely classical system. The paramagnetic response has then two possible quantum origins, either coming from permanence magnetic moments of the ions or from the spatial motion of the conduction electrons inside the material. Both descriptions are given below. Curies' law. For low levels of magnetization, the magnetization of paramagnets follows what is known as Curies' law, at least approximately. This law indicates that the susceptibility, chi_display_style_script style_chi_display style_script style_chi, of paramagnetic materials is inversely proportional to their temperature, i.e. that materials become more magnetic at lower temperatures. Curies' law is valid under the commonly encountered conditions of low magnetization, μ(BHK)BT, but does not apply in the high field/low temperature regime where saturation of magnetization occurs, μ(BHK)BT, and magnetic dipoles are all aligned with the applied field. When the dipoles are aligned, increasing the external field will not increase the total magnetization since there can be no further alignment. Polyparamagnetism. For some alkali metals and noble metals, conduction's electrons are weakly interacting and delocalized in space, forming a Fermi gas. For this material's one contribution to the magnetic response comes from the interaction with the electron spins and the magnetic field known as polyparamagnetism. Polyparamagnetism. For some alkali metals and noble metals, conduction's electrons are weakly interacting and delocalized in space, forming a Fermi gas. For this material's one contribution to the magnetic response comes from the interaction with the electron spins and the magnetic field known as polyparamagnetism. Materials that are called paramagnets are most often those that exhibit, at least over an appreciable temperature range, magnetic susceptibilities that adhere to the Curie or Curie-Weiss laws. In principle, any system that contains atoms, ions, or molecules with unpaired spins can be called a paramagnet, but the interactions between them need to be carefully considered. Systems with minimal interactions. The narrowest definition would be a system with unpaired spins that do not interact with each other. In this narrowest sense, the only pure paramagnet is a dilute gas of monatomic hydrogen atoms. Each atom has one non-interacting unpaired electron. Of course, the latter could be said about a gas of lithium atoms, but these already possess two paired core electrons that produce a diamagnetic response of opposite sign. Strictly speaking, Li is a mixed system therefore, although admittedly the diamagnetic component is weak and often neglected. In the case of heavier elements, the diamagnetic contribution becomes more important, and in the case of metallic gold it dominates the properties. Of course, the element hydrogen is virtually never called paramagnetic because the monatomic gas is stable only at extremely high temperature. H atoms combine to form molecular H2, and in so doing, the magnetic moments are lost, quenched, because of the spins pair. Hydrogen is therefore diamagnetic, and the same holds true for many other elements. Although the electronic configuration of the individual atoms, and ions, of most elements contain unpaired spins, they are not necessarily paramagnetic, because at ambient temperature quenching is very much the rule rather than the exception. The quenching tendency is weakest for F electrons because F, especially for F, orbitals are radially contracted and they overlap only weakly with orbitals on adjacent atoms. Consequently, the lanthanide elements with incompletely filled 4f orbitals are paramagnetic or magnetically ordered. Thus, condensed phase paramagnets are only possible if the interactions of the spins that lead either to quenching or to ordering are kept at bay by structural isolation of the magnetic centers. There are two classes of materials for which this holds. Molecular materials with a isolated paramagnetic center. Good examples are coordination complexes of D or F metals or proteins with such centers, e.g. myoglobin. In such materials, the organic part of the molecule acts as an envelope shielding the spins from their neighbors. Small molecules can be stable in radical form. Oxygen O2 is a good example. Such systems are quite rare because they tend to be rather reactive. Dilute systems. Dissolving a paramagnetic species in a diamagnetic lattice at small concentrations, e.g. Nd3+ and CaCl2, will separate the neodymium ions at large enough distances that they do not interact. Such systems are of prime importance for what can be considered the most sensitive method to study paramagnetic systems, EPR. Systems with interactions. As stated above, many materials that contain D or F elements do retain unquenched spins. Salts of such elements often show paramagnetic behavior, but at low enough temperatures the magnetic moments may order. It is not uncommon to call such materials paramagnets, when referring to their paramagnetic behavior above their Curie or Néel points, particularly if such temperatures are very low or have never been properly measured. Even for iron, it is not uncommon to say that iron becomes a paramagnet above its relatively high Curie point. In that case, the Curie point is seen as a phase transition between a ferromagnet and a paramagnet. The word paramagnet now merely refers to the linear response of the system to an applied field, the temperature dependence of which requires an amended version of Curie's law, known as the Curie-Weiss law. This amended law includes a term theta that describes the exchange interaction that is present, albeit overcome by thermal motion. The sign of theta depends on whether ferro or antiferromagnetic interactions dominate, and it is seldom exactly zero, except in the dilute, isolated cases mentioned above. Obviously, the paramagnetic Curie-Weiss description above Tn or Tc is a rather different interpretation of the word paramagnet, as it does not imply the absence of interactions, but rather that the magnetic structure is random in the absence of an external field at these sufficiently high temperatures. Even if theta is close to zero, this does not mean that there are no interactions, just that the aligning ferro and the anti-aligning antiferromagnetic ones cancel. An additional complication is that the interactions are often different in different directions of the crystalline lattice, anisotropy, leading to complicated magnetic structures once ordered. Randomness of the structure also applies to the many metals that show a net paramagnetic response over a broad temperature range. They do not follow a Curie-type law as function of temperature, however, often they are more or less temperature independent. This type of behavior is of an itinerant nature and better called polyparamagnetism, but it is not unusual to see, for example, the metal aluminium called a paramagnet, even though interactions are strong enough to give this element very good electrical conductivity. Superparamagnets. Some materials show induced magnetic behavior that follows a Curie-type law, but with exceptionally large values for the Curie constants. These materials are known as superparamagnets. They are characterized by a strong ferromagnetic or ferrimagnetic type of coupling into domains of a limited size that behave independently from one another. The bulk properties of such a system resembles that of a paramagnet, but on a microscopic level they are ordered. The materials do show an ordering temperature above which the behavior reverts to ordinary paramagnetism, with interaction. Ferrofluids are a good example, but the phenomenon can also occur inside solids, e.g., when dilute paramagnetic centers are introduced in a strong itinerant medium of ferromagnetic coupling, such as when Fe is substituted in TlCu2Se2 or the alloy OFe. Such systems contain ferromagnetically coupled clusters that freeze out at lower temperatures. They are also called mictomagnets.
Please subscribe and thanks for watching.